Welcome to the ARENA online seminar for this week. My name is Tyler Gorda. I'm the host. I'm a postdoctoral researcher at the TU Darmstadt in Germany, working on high density quark matter things. And this week we're happy to have Carolyn Raithel here to present her work on probing the dense matter equation of state and neutron star mergers. Carolyn is a joint postdoctoral fellow at the Institute for Advanced Study, the Princeton Center for Theoretical Science, and the Princeton Gravity Institute for Initiative. She received her PhD in astronomy and astrophysics at the University of Arizona in the summer of 2020. And Dr. Raithel's research is focused on understanding the exotic nuclear physics that governs the interior of neutron stars using astrophysical observations. And recently, she has been particularly interested in how the dense matter equation of state impacts gravitational waves emitted by neutron star mergers. One final thing before we begin is that Carolyn says she's fine with people interrupting if they have a pressing question, if something is unclear during the talk, so just feel free to say something or post in the chat at any point and I'll keep an eye on it. And after the talk, we'll have an informal sort of hangout in Gather Town. There will be a link placed in the chat during the talk, and feel free to join that for a more informal discussion at the end. So Carolyn, we're very interested to hear your talk and feel free to begin.
Great, thank you for the introduction, and thanks very much for the opportunity and for everyone who's calling in today. I see a lot of familiar names and a lot of experts in this field, so I'm really pleased to have the opportunity to share with you all, as Tyler said, some of the work I'm doing, trying to understand how we can use this new probe that we have of binary neutron star mergers to try to probe the properties of the dense matter equation of state. And so just by way of introduction, let me start by pointing out the particular part of the parameter space that I'm referring to when I'm talking about using neutron star mergers and neutron stars in general to study the equation of state. So as you all know, neutron stars are the remnants of quark-lap supernovae. They have masses between typically 1 and 2 times the mass of our sun, so on the order of 10 to the 33 grams. And these are compressed to stellar objects with radii between, say, 10 and 13 kilometers. And so with this kind of extreme compression factor, the central densities that are reached in the core of neutron stars are very extreme. They can exceed 10 to the 15 grams per cubic centimeter, or equivalently up to around 6 or so times nuclear densities. Additionally, for beta equilibrated neutron stars, the matter is extremely neutron rich, with neutron excess parameters exceeding 90% at some densities. And from very soon after the time the neutron star is born, it cools very rapidly. So the matter is thermodynamically cold, meaning that the average energy of the particles is much lower than the local Fermi energy. And so for isolated neutron stars, we treat the matter as if it's at 0 temperature. In my talk today, I'm going to discuss how we can deviate along the temperature axis from these conditions. But this is kind of the general part of the parameter space we're talking about when we're talking about the neutron star equation of state. Very high densities, very neutron rich, and typically cold, but can be heated during the course of these neutron star mergers. Okay, and so when it comes to probing this particular part of the parameter space, this is essentially inaccessible with at least the current generation of ground-based nuclear experiments. So really the only way forward is through observations of neutron stars. And in particular, as I've said today, my talk is going to focus on this new probe that we have through binary neutron star mergers, and in particular the gravitational waves that are produced by these mergers. And so to start with, this is a summary slide showing the current status of gravitational wave observations that the LIGO-Virgo and now COGRA collaborations have made over the last 7 years since the first detection in 2015. So in this figure, each of the pairs of points connected by an arrow represent one merger event. So the latest catalog had 90 plus events that were detected. Although as you can see from this figure, most of these mergers to date have been binary black holes. There are a much smaller but growing number of events that contain at least one neutron star, including now 2 confirmed binary neutron star mergers, as well as 2 confirmed neutron star black hole mergers, and a few other kind of lower significance events, or events where the identification of the lower mass object as either a neutron star or black hole is less clear. And so in order to understand how we can extract equation of state information from the gravitational waves from one of these events, let me show you kind of a schematic of what is happening to the neutron stars during the course of this merger. So in the top figure here, this is just showing the plus polarization of the gravitational wave strain as it would be detected, say, by a LIGO detector. And I've denoted kind of the 3 different regimes I want to focus on. And on the bottom are snapshots from one of my simulations showing the matter of the 2 neutron stars as they merge together. So very early on in the neutron star merger, the neutron stars are well separated, still spherically symmetric, slowly orbiting one another. As they orbit one another, they will emit gravitational radiation, which causes the orbit to shrink and to accelerate. As the neutron stars get closer together, they become increasingly tidally deformed, which further accelerates the inspiral. Once the neutron stars come into contact with one another, there's a very violent and turbulent merger phase, following which, if the neutron stars that merge are light enough so that they don't immediately collapse to a black hole upon merging, there can be a continued phase of post-merger gravitational wave emission following the merger. And this is sourced by the oscillations of this rapidly rotating, non-axisymmetric massive neutron star remnant as it relaxes down to some equilibrium configuration. As you can see, these are at much higher frequencies than the inspiral gravitational waves. So as a result, essentially all of our current gravitational wave constraints on the equation of state have come from measurements of this inspiral. We have not yet measured these post-merger gravitational waves, and I'll show you why on my next slide. But for now, let me just say that these current gravitational wave constraints come from essentially from the measurement of the tidal deformability parameter of characterizing the neutron star matter by measuring kind of the phase evolution of the inspiral portion of the gravitational waves. And so primarily from the first merger event, GW170817, which is still our loudest and highest SNR event to date, we have gotten some really exciting new constraints on the dense matter equation of state from this tidal deformation measurement. In my talk today, though, I want to focus instead on what new or additional physics we might be able to learn with a future detection of this post-merger gravitational wave signal. And so this will be the focus of my talk today, is kind of the forward-looking questions of how we can measure the equation of state, or what information about the equation of state we can glean from such observations. And these observations are very highly anticipated. As I just said, they haven't yet been detected because they're at much higher frequencies, typically between 2 and 5 kilohertz, depending on the equation of state. And this is a part of the space here where the LIGO sensitivity curves, the sensitivity curves of any gravitational wave detector, increase pretty rapidly. And so it may be possible, depending on who you ask, to make a measurement of these post-merger gravitational waves with advanced LIGO at design sensitivity with a sufficiently nearby source. But even if this proves to be too challenging for advanced LIGO, more conservatively, this will hopefully happen in the coming decade or so with the construction of the next generation of facilities, like Cosmic Explorer, which is the US-based proposal for the successor to LIGO, or Einstein Telescope, which is the European-based proposal. But in either case, hopefully these measurements will be coming in the coming years. And so the outline for my talk today is going to be focused on the central question of what additional equation of state constraints will we be able to gain from observations of this post-merger phase of the merger evolution. And in particular, I want to discuss a model that I use for parametrically constructing neutron star equations of state that we can use in these merger simulations for systematic and targeted studies of particular parts of the equation of state parameter space. And I will discuss in particular 2 different studies using this framework to explore different uncertainties in either the finite temperature part of the equation of state or the cold part of the equation of state parameter space. Okay, and so before I get into the details of that, I want to zoom way out and just highlight kind of what the big picture philosophy of this approach is, because there's a lot of different ingredients to this big picture goal of trying to constrain the equation of state using gravitational wave detections. And so really the philosophy behind this approach is a forward modeling approach, where if you start with a theoretical model for the equation of state, which can be a microphysical model like many of the people in this collaboration are working on, or something parametric like I'll show you today, to understand how this is going to influence, say, a gravitational wave signal, we need to input this into a numerical simulation in full general relativity, where we're simultaneously solving the equations of hydrodynamics and the Einstein equation to dynamically evolve the space-time. And in this way, we can predict the properties of a neutron star merger for a given model of the equation of state. And so we can then predict properties like the gravitational wave emission or the amount of ejecta that is launched, which is then available to fuel an electromagnetic counterpart alongside this event. And then we can compare these predictions to the actual observations that LIGO makes or that we would have from our X-ray telescopes, say, of the kilonova evolution and so on. And then we can use this then, of course, the agreement between the predictions and the observations to go back and constrain our models for the equation of state. So this is sort of the big picture approach. And the part I'm going to be talking about today is at the interface between these first two boxes. Okay. And so that takes me to this first main topic that I want to discuss, which is a model for constructing parametric finite temperature equation of state models to study this post-merger evolution. And I'm emphasizing here that these are finite temperature equations of state, because when it comes to modeling the post-merger evolution, we're really, we're really studying a different part of the parameter space than is probed during the inspiral. As I mentioned in my opening slide, isolated neutron stars are thermodynamically cold, and so we can model them as if they're at zero temperature. And so in this regime, the equation of state is just a one parameter model where we can describe it purely as pressure as a function of the density. And this assumption of cold equilibrium neutron stars is a reasonable assumption through essentially the early parts of the inspiral, up until the point at which the neutron stars come into contact with one another, at which point there's significant shock heating that can raise the temperature of the system to some tens of MeV, at which point the thermal pressure can be dynamically important, as I'll show you, in influencing the evolution of this post-merger phase, or the dynamics of the post-merger phase. And so to accurately capture the physics in this regime, we need the full 3D information on the equation of state, how it depends on the density, temperature, and additionally also on the composition, the proton fraction. So there are a large and growing number of existing finite temperature equation of state tables that we can use to try and study this mapping from the equation of state to the merger properties that I was describing. In this slide, I'm summarizing the properties of some of the more commonly used finite temperature equation of state tables that you see in the merger literature. This is by no means exhaustive, but for various historical reasons, these are kind of the more common ones you see in the merger literature. And the first thing I want to point out is when we at least focus just on this subset of models, there's a somewhat limited coverage of the possible parameter space. So the figure on the left is showing some of the zero temperature properties of these equations of state, in particular the mass radius relations. And in particular, you'll notice that none of these models predicts neutron star radii that are smaller than 12 kilometers. Even though we now have some growing observational evidence, for example, from GW 17817, providing significant evidence that the neutron star radius may be between kind of in this smaller part of the parameter space. GW 17817 has suggested that the neutron star radius is between 10 and 13 kilometers, with kind of more support for stars less than 12 kilometers. So we're kind of missing out on one part of the parameter space if we limit our studies to just this sample of equations of state. In addition, these models vary in multiple ways simultaneously, which can make interpreting the differences between merger simulations that use different models difficult. So these models differ not only, for example, in their zero temperature properties, such as the characteristic radius of the neutron source and the maximum mass, but they also differ to a smaller degree in the finite temperature part of the equation of state, which is what's shown on the right here. This is showing the thermal pressure at a fixed temperature for the same subset of models. And we find that you can see here there are differences of 3 to 5 times in the thermal pressure predicted by these different models for matter at the same temperature. And so this just makes it a little more difficult to systematically compare the merger outcomes that you get when you're comparing between two of these different equations of state, because you have multiple moving pieces that are changing simultaneously between these different models. And so to get around some of these limitations, the approach I take in my research is to use a parametric approach for calculating the equation of state at arbitrary temperatures, densities, and proton fractions. And so in very schematic cartoon form, I have listed above here what this looks like. And this is really a very simple series expansion approach in which we start with a model for the cold beta equilibrated equation of state. And this can be a microphysical model for the equation of state. It can be something informed by astrophysical observations, or it can be a completely agnostic representation of the equation of state, like some piecewise polytropes that are designed to step through some interesting part of the equation of state parameter space, say to model 10-kilometer neutron stars. We add to this a thermal correction term that lets us extrapolate to finite temperatures, and a composition-dependent correction term, which allows us to extrapolate to non-equilibrium compositions. I'm not going to talk about this second term at all today, but I'm happy to chat more later if people are interested. This is just based on some parametrization of the nuclear symmetry energy. But I want to focus today primarily on this thermal part of the equation of state. And in particular, the goal of this model that I'm going to show you is to come up with a reasonable functional form for parametrizing the thermal pressure here that includes the relevant physics across multiple different density regimes, crucially including the leading order effects of degeneracy, which become important at densities above the nuclear saturation density, which is where most of the matter within the neutron star lies. And as you can see here in this schematic, in this high density regime, when you have to take into account these effects of degeneracy, it leads to a significant density dependence in the thermal pressure model. Let me make a quick comment for the experts in the audience who are probably recognizing that what I have here in the box equation is very reminiscent of the hybrid approach, which has been used in merger simulations for many years. And that's because this is taking the exact same philosophy of the hybrid approach, where you want to add on a thermal correction term to any cold equation of state. But in the hybrid approach, the model for the thermal pressure term fixes the thermal index to be a constant value, which is basically analogous to neglecting the effects of degeneracy or extrapolating the ideal fluid-based approximation to very high densities. And this has been shown to lead to significant errors in the gravitational wave signals that you observe. So our approach here is to keep the philosophy of this hybrid approach, but to move beyond it and to add in some this more accurate density dependence at high densities, and to include these effects of degeneracy in our model for the thermal pressure. And so to write down a functional form for the thermal pressure that is general and can be added to any cold equation of state, we turn to a Fermi liquid theory-based approach, in which the thermal pressure in this degenerate regime can be written down as a function of the density, the temperature, and functions of the level density parameter, which in turn depends on the particle effective mass, which is here called m star. And so to generalize, to create a general parametric function here, what we do is we introduce a parametrization on the effective mass function, which just is a simple 2-parameter model, which takes advantage of the asymptotic behavior of the effective mass function, where at very low densities, this just approaches the the vacuum rest mass of the particles, and at higher densities, the effective mass function decays as the interactions between the particles start to become significant. And so we parameterize this, like I said, with a 2-parameter model related to a density-dependent parameter that characterizes the density at which the effective mass function starts to decrease, and a power law parameter that characterizes the rate of this decay. We find that with this 2-parameter model, we're able to accurately recover the density dependence of the thermal pressure in this high density regime, which is what's shown in the figure on the right here, where the diamonds in this figure are showing the prediction of one of those tabulated microphysical finite temperature equations of state. And the solid line is our parametric model for the thermal pressure using just this 2-parameter model for the effective mass function. And so you can see we're able to accurately recreate this density dependence in the high density regime for a range of types of temperatures you expect to find in a merger simulation. And so this is showing us that, at least at the analytic level, that this framework for constructing this thermal pressure model does a reasonable job at recreating the predictions of one of these microphysical equations of state. We can also see that this is a good approximation in the context of a full merger simulation as well. And this is some ongoing work that's wrapping up at the moment with Pedro Espino and Vasilis Paskalidis, where we designed a stress test to try and test the M-star framework for constructing these parametric equations of state, like I said, in the context of a full merger simulation. And so the idea behind this is we took an existing finite temperature equation of state, the SFHO table, for those of you who are familiar with it, and we took the 1D zero temperature beta equilibrium slice of this equation of state, and we got rid of all of the composition and temperature dependent dimensions of this table, and we replaced them with this M-star framework for modeling the finite temperature and also composition dependences of the equation of state. And then we simulated a complete merger simulation with both the full SFHO table and this approximate reconstruction to confirm that the small residual errors in our modeling of this thermal pressure and composition dependent terms do not propagate to larger errors in merger outcomes. And what we find is that indeed this is the case, that we are able to recreate realistic merger properties with these approximate equation of state tables. And so what's shown here is just the thermal profile of the neutron star merger remnant at the very end of our simulations. And we find that these approximate equation of state tables are indeed able to accurately recreate realistic thermal profiles for remnant neutron stars that are formed during the neutron star merger. And we also can compare the gravitational wave signal that you get from such a simulation, where the figure on the left is showing the strain, and on the right is the power spectrum of these gravitational waves. And again, we find that these signals are virtually identical. So again, confirming that these approximate equations of state are sufficient to accurately reproduce the gravitational wave signals of more realistic models in the context of full merger simulations. Okay, so with this framework now in hand, we can start to use this to explore new parts of the equation of state parameter space, or to perform very specific targeted studies of particular parts of the parameter space. And so in particular, let me now turn to a study that I performed last year, trying to explore uncertainties in the finite temperature part of the equation of state, with the goal of trying to be able to start to disentangle the role of the cold equation of state from the finite temperature part of the equation of state and determining these merger observables, which is an important step to better understanding kind of this mapping between the equation of state and merger properties. And in particular, if we want to ultimately combine the types of equation of state constraints we're getting from this post-merger phase, which is probing the finite temperature part of the equation of state, with inspiral constraints, which is probing the cold equation of state, we need to better understand this mapping and how the two sources of uncertainty can be influencing merger outcomes. Okay, so to that end, we performed a study with 4 different neutron star merger simulations, which were all governed by the same zero temperature equation of state, which is based on the nuclear model ENG. But to each of these merger simulations, we painted on a different thermal extrapolation term using a different set of M star parameters, which were designed to bracket the range of uncertainty in the finite temperature part of the equation of state. And we performed then simulations for each of these different setups, again in full general relativity. And I'll show you here an animation of what these mergers look like. So on the left is going to be the evolution of the density profiles of the 2 neutron stars as they merge. And on the right is the thermal pressure relative to the cold pressure. And so this is normalized in this way so that you can see visually when the thermal pressure starts to become a significant fraction of the cold pressure. This is a proxy for telling you when it's may become dynamically important for influencing the evolution of the merger. So as you can see, the neutron stars start at 0 temperature. This is what we prescribe at the beginning of our simulations. And indeed, they remain essentially cold, except for some spurious heating in the atmospheres, up until the merger itself, at which point there was that strong shock heating at the merger interface. And so by late times, as this remnant sort of relaxes down to a more spherically symmetric configuration at late times, you can see that the thermal pressure is indeed a significant fraction of the cold pressure at relatively high densities in the neutron star interior. And I'll show you that a little more quantitatively in a few slides. So this was with one set of these effective mass parameters, or one extrapolation along the thermal dimension. We can now compare these late time snapshots from the merger simulations for the different sets of M-star parameters that we explored in this study. And I'll go ahead and highlight some of the main trends that we're finding here. So in particular, we do find that there's small differences in the thermal pressure that is reached depending on how you parameterize this effective mass function. In particular, we find that this density dependent parameter, which characterized the density at which the effective mass function started to decrease, is most directly governing the thermal pressure profile in the outer layers of the star with higher values of this density parameter leading to higher thermal pressures. We can also compare the temperature snapshots of these same merger remnants, which are shown here on the bottom. And we find, again, a bifurcation of the results with, in this, which depend more sensitively on the power law parameter alpha, with larger values of alpha leading to higher temperatures reached in the inner core of the remnant, and lower values of alpha leading to lower temperatures in the very innermost region of the remnant. And so these are kind of preliminary indications of how the uncertainties in the finite temperature part of the equation of state are influencing the thermal structure of the neutron star merger remnant. And I say they're preliminary because we have just 2 free parameters and 4 sets of simulations here where we're trying to draw some insight from. But this is really giving us a first look into how these uncertainties are mapping to the outcome, the thermal properties of this remnant. These are showing just the spatial slices of the remnant, equatorial spatial slices of the remnant. We can also look at how the thermal pressure and temperature vary as a function of density within the remnant. These are median properties plotted as a function of density within the star now. And the first thing I want to point out here is that the thermal pressure is indeed a significant fraction of the cold pressure to quite high densities within the remnant star. So the thermal pressure exceeds 10% of the cold pressure at densities of up to 2 to 3 times the nuclear saturation density. And again, we find differences of 3 to 5 times in the thermal pressure that is reached in the dense matter interior, depending on what you assume for this finite temperature extension. And likewise, we find differences of factors of 2 or so difference in the temperatures. And it might seem redundant to be talking about thermal pressure and temperature separately, but I'm highlighting both of these just because these are giving different insight into how different properties of the evolution might be affected by these uncertainties. So in particular, the thermal pressure, because it's contributing to the overall pressure budget of the remnant, is going to influence properties such as the oscillation modes of this remnant and thus the gravitational wave emission, which I'll show you on the next slide, whereas the temperature profile of the remnants are going to more effectively, more directly affect properties such as the neutrino emissivities, which if the remnant survives for long enough can affect the cooling or radiation of the subsequent disk. But let me show you here directly what the gravitational wave signals look like as one of the most directly observable properties from these merger simulations. You'll see right away that the inspiral portion of these gravitational wave strains that we extracted from the simulations are indeed identical between these 4 simulations that we ran, which is what we expected, given the fact that these all were governed by the same zero temperature equation of state. And we saw that the 2 neutron stars remained essentially cold up until the merger. So the differences between these thermal treatments is only really activated in this post-merger phase. But here we do indeed see some differences in the post-merger signal, in particular in kind of the beat frequencies of this decaying signal, which is related to the oscillation modes of the remnant. So what we find is hints at at least a subtle signature of these M-star parameters on the post-merger gravitational waves, which I think is kind of a tantalizing possibility to explore whether or not this would ever be a measurable signal, because this is a part of the equation of state parameter space that would not be directly accessible from studies of the inspiral alone or from studies of isolated cooled neutron stars alone, but that we might be able to probe with future detections of these post-merger gravitational waves. We're currently doing some follow-up work on this right now, extending this study to look at also different cold equations of state and explore this kind of parameter study in the finite temperature part of the equation of state to get a more complete coverage of the overall parameter space. So hopefully we'll have an update on exactly how measurable such a signal might be. Or I'll say for now, it seems like it might be a subtle effect, but we are seeing some indication that this persists across different cold equations of state as well. Okay, so for the last part of my talk, I want to discuss a different type of study now, using this same framework for constructing parametric equations of state, but now using it to study new parts of the cold equation of state parameter space. And in particular, to do so, I need to introduce one more concept, which is actually one of the main goals of trying to measure these post-merger gravitational waves in the first place, which is the goal of performing asteroseismology on the remnant of one of these neutron star mergers. And in particular, the idea is that if you take the spectrum of these post-merger gravitational waves, so effectively compute the Fourier transform, you get something that looks like the figure on the right here, where you can identify distinct spectral peaks. And these spectral peaks have been correlated with different oscillation modes of the neutron star remnant. So for example, this dominant spectral peak here, F2, which I'll talk more about for the rest of my talk, is powered by the quadrupolar oscillation modes of the remnant neutron star. And this is a robust feature that is found in essentially all merger simulations for any equation of state. But what changes here is that as you swap out for different equations of state, this spectrum shifts to the left or the right depending on the equation of state. And it does so in a very characteristic way. And this has been studied over the last decade or so, and this has led to the empirical determination of several universal or quasi-universal relations between the location of this spectral frequency, F2, and different properties of the neutron star equation of state, such as the neutron star radius. So the figure on the left here is from a very recent meta-analysis of over 100 different merger simulations with different binary parameters for the 2 neutron stars and different equations of state by Retneris et al. And they showed here, which again has an idea that has been around since early work by Stereulis and Brauswein in the early 2010s, that this peak frequency F2 correlates very strongly with the neutron star radius. And so if you fix the binary parameters of the system, you get a projection that looks like the figure on the right here, where there's effectively a one-to-one mapping between this peak frequency and the neutron star radius at a fixed intermediate mass. So this notation just means the radius of a 1.6 solar mass neutron star. And this is a very powerful tool because if we can characterize the errors of this relationship sufficiently well, this allows us a way to take a measurement of these future gravitational, future measurement of these post-merger gravitational wave signals and map it directly to constraints on the neutron star radius, which we can then map back to the equation of state. So for example, if LIGO measures that this peak frequency F2 is 3 kilohertz, we can immediately read off using this mapping that the neutron star radius must be about 12.5 kilometers, and conservatively that it's between 12 and 13 kilometers. Now, the one way that this has been shown to be violated previously is in the case of an equation of state that predicts a first order phase transition at high densities. And this was shown by Bauswein et al. In 2019 PRL, that if the equation of state has a first order phase transition, then you will systematically violate this quasi-universal relation with F2 leading to higher values above what this relationship would normally predict. And so if you had a simultaneous measurement of F2 and say constraints on the radius, say from inspiral observations on the constraints on the tidal deformability, and you found a point that violates this existing quasi-universal relation, the claim of this paper is this would be a smoking gun indicator of a first order phase transition in the matter. So in the last piece of work I want to discuss today, I'm going to discuss a paper that was recently posted on arXiv that I did together with Elias Most, who's also a postdoc here at IAS in Princeton, which was in part a follow-up to a work we had out last year together, trying to understand kind of more generally the conditions under which this quasi-universal relation breaks down. And to do this, we wanted to try to explore a wider range of phenomenology in the equations of state that we wanted to use to try to reconstruct these universal relations than is often considered in the merger literature. And so we constructed a sample of equations of state. These are parametric equations of state, piecewise polytropic equations of state, that were designed to systematically sample extreme slopes in the mass radius relation. And in particular, we constructed these systematically so that we would have subsets of models that, for example, all predict neutron stars with common either compactnesses or tidal deformabilities. So for example, here we have 3 models that all predict neutron stars with 12 kilometer radii, but with very different mass radius slopes. And to give you a sense of kind of the motivation behind these different phenomenological structures in the mass radius relation, these red curves, which are indicative of models that predict more compact neutron stars at high masses. These are the types of phenomenology that you would expect to see, for example, from equations of state with some sort of crossover phase transition at high density, some softening of the equation of state at high densities, whereas these blue curves are where you predict larger neutron stars at high masses are the predictions that you might expect for an equation of state that stiffens at high densities, which can be found for more exotic forms of matter like quark ionic matter appearing. So we constructed these parametric equations of state, and we painted on the same finite temperature extension to all of these models using an intermediate set of m-star parameters, which was, I think, an important step to help us rule out differences in the finite temperature part of the equation of state as the source of any of the subsequent trends that we were finding. And of course, then we simulated merger simulations with each of these different equations of state. Whoops. And these are a subset of the gravitational wave signals that we found from these simulations, where I'm picking out just one of our sort of forward bending mass radius relations and one of the backwards bending mass radius relations for 3 different compactnesses of neutron stars. So if I focus in particular on the set of models that predict neutron star radii with 12 kilometers for an intermediate mass neutron star, you can see here that there are significant differences in these post-merger gravitational waves. In particular, the beat frequencies here, which are indicative of these oscillation modes of the post-merger remnant, differ significantly for these two models which have the same characteristic radius, which seems to be in violation of the idea behind this universal mapping between F2 and the radius of an intermediate mass neutron star. And indeed, if we identify what this peak spectral frequency is for each of these models, and we compare them against the existing quasi-universal relation, we do see a much larger scatter than has previously been reported, with a scatter of up to 600 Hertz in this spectral frequency F2 for stars with a common radius. But I think more importantly than the larger scatter is the fact that these blue points, which correspond to models, again, that have higher mass neutron stars leading to larger radii, are systematically violating the existing quasi-universal relations. And what we find is that you can actually characterize the scatter of these results very robustly using now a 2-parameter model that depends additionally on the slope of the mass radius relation. So whereas before these quasi-universal relations were typically written down as a monoparametric mapping between this peak frequency F2 and the radius, here we're finding statistical evidence suggesting that there needs to be some additional dependence on the structure of the mass radius relation, the slope of the mass radius relation. And so the conclusion behind this work is that these post-merger gravitational waves are actually simultaneously probing a combination of both the neutron star radius and the leading order slope of the mass radius relation. And the implication of this statement is that this peak frequency F2 is actually probing the matter of the neutron star at slightly higher densities than has previously been considered. The idea behind this being that if we could uniquely describe this mapping just in terms of the properties of some lower density neutron stars, some lower mass neutron stars, this would imply that we're only need to be sensitive to the equation of state up to kind of intermediate densities of 1 to 2 times the nuclear saturation density. The fact that we have to take into account what is happening at higher masses in the mass radius relation is telling us that the higher density equation of state is also playing a role here. And so this raises, I think, kind of an exciting possibility that if we get high precision, high SNR joint observations of an event, of a future merger event from the inspiral through this post-merger phase of the gravitational wave evolution, it may be possible to actually constrain the equation of state across a range of densities from this single event, where the inspiral is going to give us constraints on the tidal deformability, which is primarily constraining the equation of state at densities of 1 to 2 times the nuclear saturation density, very roughly, and the post-merger phase is probing slightly higher density physics. Okay, and so with that, I will wrap up and just kind of summarize quickly by saying that I think we're at an exciting time in our studies of the equation of state, trying to constrain the equation of state with gravitational waves. LIGO will turn back on this December and will hopefully give us many new measurements of the tidal deformability from inspiral observations of gravitational waves, which we can use to kind of develop increasingly stringent constraints on the equation of state. But hopefully soon we will also get new constraints coming from the future detection of these post-merger gravitational waves. And I think that mapping these signals back to the equation of state really requires systematic construction of these numerical simulations to do targeted parameter studies to develop this mapping between how varying the equation of state is going to change the predicted properties of the merger. And so I discussed today one approach that we can take to try and tackle this problem, which is what I use in my research, which are the construction of these parametric finite temperature equations of state. There are other methods that people are using to try and tackle this problem, but hopefully we'll have some data to start testing these predictions coming soon. So with that, I will conclude and happily take any questions. Thanks.
Thank you very much, Carolyn, for this very informative talk with a lot of very interesting results and nice systematic explorations that you've done. So we're open for questions now. If you have a question, please just raise your hand in Zoom and I will call on you when I see someone. Perhaps while people are thinking, I can ask a question first. So would you be able to give a little bit of the details of what goes into your merger simulations that you perform, such as like what physics is included or what is not and how it's handled?
Yeah, good question. I did not get into any of these details at all. So there's, I guess there's two components. So for the finite temperature, well, okay, let me just try and address this more generally. Right, these are full numerical relativity set simulations, and but we are studying non-magnetized neutron stars, so we do not have magnetic fields. The finite temperature explorations that I was discussing today also do not have neutrinos. We're assuming that the matter is remaining in equilibrium throughout, which is an assumption. The study at the end with the quasi-universal relations does have, those simulations do have a neutrino leakage scheme involved. Those are two of the main ingredients: no magnetic fields throughout, neutrino leakage scheme in the last set of simulation results that I showed you. As far as the other physics that are included, do you have something in particular in mind?
No, I was mainly interested in hearing about the neutrinos in particular,
Yeah.
so that was helpful.
Thanks.
Okay, thank you. So I see a question now from Atul. You can unmute and ask your question, please.
Yes. Hi. I have a question about like the initial part of the talk, basically, where so I'm just wondering if there's any comparison done between a tabulated equation state based merger simulation where with the gravitational waveform taken out, extracted, and that compared to a cold equation of state, but then with a gamma thermal based thermal component.
Yes.
Yeah.
Yes, absolutely. So yes, the first person to look into this was Andreas Bauswein. He has a really nice 2010 paper where he compared the merger simulation outputs, the gravitational waves, and also ejecta properties for either a tabulated equation of state or where they, like you said, replaced the finite temperature component with a constant gamma thermal index. And they showed in that work that this leads to, I'm gonna not remember the numbers off the top of my head. I think it was like 250 hertz differences in the location of that peak spectral frequency of the post-merger gravitational waves, and also significant differences in the ejecta as well. So yes, that has been known for some time, that using the constant gamma thermal leads to some errors in the post-merger evolution.
I see.
There have
and
been some
are those
papers also? I think there's one by Figura et al. We included some constant gamma thermal analyses in our 2021 paper on this also.
Okay. And are those frequencies, the 250 hertz or so movement, is that towards the lower frequencies or higher? I would assume it be, which way should it go?
That's a good question. I don't have,
because it's becoming softer in some sense. So
so I think in the Bauswein paper, I don't remember what direction it went in off the top of my head, because they looked at both pretty soft, like gamma of 1.5 maybe, and gamma of 2. Yeah, I would check. It's a 2010 paper by Andreas Bauswein where they looked into this.
2010 Bauswein. Okay, thank you. Yeah.
I see another question in the chat. Feel free to unmute and ask your question. Behan. I at least don't hear anything. Does anyone else hear anyone speaking?
I also do not hear.
Okay, I'm sorry, but we can't hear you. It looks like you are unmuted. We don't. Oh, I see. We posted in the chat.
Are you waiting for me?
No, sorry. There was another question and we couldn't
Okay.
hear them. So the question in the chat has been posted. I'd like to ask what are the resolution of the simulations and how the findings were affected by different resolutions, and whether the pi symmetry was used, which has been suggested to affect the development of one-arm spiral instabilities, which in turn affects the gravitational wave form.
Okay, so for the finite temperature studies, the resolutions were such that we spanned the diameter of the initial neutron stars with about 100 grid points, which is, I think, usually a typical resolution that you have for these kinds of simulations. We additionally, we performed a resolution study in that paper. And actually, I have a new paper where we are improving some of the convergence properties of the merge revolution, which we'll have with some updated explorations coming out soon. So for the initial paper, the finite temperature study that I showed you, we don't have strict convergence in the post-merger gravitational waves, but what we do have is a strict convergence during the inspiral, and that the differences between the post-merger gravitational waves as we increase the frequencies are extremely small. But we're doing kind of some follow-up studies on this with, like I said, some improving the convergence behavior, which actually is going to be a paper hopefully on arXiv early next week. As for your other question about what symmetries we imposed, so we did impose symmetry across the Z dimension just to accelerate the inspirals. But for the one-arm spiral, I'm not sure if that was your question or about the one-arm instability. So those for the finite temperature studies anyway, those were all equal mass neutron star mergers, for which you typically don't see the emergence of a strong m=1 mode. For the study I showed at the end with these kind of extreme mass radius slopes, those had slightly unequal non-unitary mass ratios, but we haven't looked into the one-arm instabilities for those at all yet.
Okay, thank you. Mark Alfred, you may ask your question now.
Thanks. So I just wanted to understand this M-star framework. So when you matched it to SFHO,
yeah,
right? So how did you make it agree? Like, did you look at SFHO's prediction for the effective mass and you tuned your parameters to agree with that?
Yes, exactly.
Okay.
So we use the effective mass functions for the tabulated equations of state, and we provide in our 2019 paper, we provide the fit parameters for this sample of 10 or so, commonly used equations of state that we had the available effective mass functions for. And so in this comparison against SFHO, we are using the best fit parameters for the effective mass function to do this comparison.
Okay, so in that case, it's not clear to me how it lets you generically add the finite temperature part of an equation of state, because if somebody hands you an equation of state, like it seems like either the equation of state already knows its finite temperature part and you're fitting it, or it doesn't know its finite temperature part, in which case, I guess, I mean, if it knows its effective masses, doesn't that sort of, well, okay, so you're fitting to the effective mass dependence at 0 temperature. Is that what you're doing?
So we fit simultaneously at to the effective mass functions at 1, 10, and 50 MeV.
Right.
We find very small differences in temperature, so we're neglecting differences in temperature.
Okay, so SFHO sort of doesn't need your help, right? Because it already knows what its pressure and everything is at finite temperature. So what do you? So I'm just trying to work out, when would you use this framework?
So this framework you would use if you want to construct a new parametric equation of state to step through some new part of the parameter space. Say I want to explore some piecewise polytropic model that lets me predict 10-kilometer neutron stars. So I have some piecewise polytropic model, and I want to add on something that has reasonable density dependence in the thermal pressure function, something that's much better than a hybrid model that isn't capturing any of the degenerate physics. Then I will use this model to paint on a finite temperature part using some intermediate set of M-star parameters.
But
so
you'll just have to sort of make up some M-star function that has no particular relation to the physics of that model. It's just, you could choose a whole range of them.
Correct. So we
Okay.
are assuming that the cold and finite temperature parts are separable in this model, which is an assumption. I think it's a reasonable assumption, but it's an assumption. And what the goal partly of these parameter studies for the M-star models is to understand how much freedom really is there. We can bound what these parameters are based on some combination of experimental constraints and what is spanned by the existing sample of models that people are considering. We can look within those ranges and see how much variation do you get in the subsequent evolution. If you find no differences across some range of these parameters, then we know the results are insensitive to the choice of the M-star parameters. You can pick anything and carry on. Otherwise, there is some uncertainty and you need to take this into account in the subsequent analysis.
Okay.
Is that?
Well, I just suspect that you could, do you have an example where that is actually constraining? Because I kind of suspect you could choose a lot of different mass functions and get a lot of different thermal extensions of polytropic equations of state. I kind of...
You mean the density dependence here, the model, or what parameters we're fitting to this particular model?
Well, I just meant what you get out in the end as a finite temperature equation of state. I would have thought there's quite a lot of wiggle room if the physics of the model itself isn't constraining what you do, then I'd have thought you could, even within this framework, you could get a lot of different thermal extensions of a given equation of state.
So I mean, this is what we're trying to analyze. At least, we are taking kind of bracketing. We have two free parameters in this model. We're bracketing what the values can be, and this is the range of outcomes that you get for the thermal properties of the remnant for one cold equation of state. You're right. Maybe if you explore within these, there's going to be more differences. But I don't think it can vary. And I think this study is hopefully trying to bracket the range of possibilities you can get for exploring an extreme range of M-star parameters.
Okay. Okay.
Thanks for the questions.
So are there any remaining questions? I don't currently see any. If you have something you want to ask, please raise your hand. Yes, I see another hand now. I'm sorry, I can't pronounce your name, but you can feel free to unmute and ask your question.
Hi, I just have a pretty naive question. So, like you said, you're fitting your M-star to SFHO. Why can't you just use SFHO? Like, what's the difference? Like, just why do you need to do that?
That was purely intended as a validation. Yes, if you want to use SFHO, this gets back to Mark's question also, you should use the table for SFHO. That was just intended to confirm that the approximations and the simplifications that we have introduced with this framework are not going to drive our merger simulations to some very different solution than what we expect.
Okay.
So it's just a proof of principle to further kind of validate the framework that we can with these simplifications recreate the full predictions of a realistic equation of state.
But so do you need to like validate for other quantities like I don't know, like pressure or like entropy or whatever others? So you only fit your M-star, your mass to what SFHO has, but what about other parameters? Are they going to agree with SFHO or?
So the model.
Or go ahead.
Do you mean other equations of state or other properties within SFHO?
Right, other properties within SFHO.
Yeah, so we calculate the pressure model is the M star part comes into just constructing the thermal pressure in the degenerate regime, but we have a full model for the pressure, and we derive the energy functions analogously in a consistent way, and the sound speed and everything else.
Mm-hmm. Okay, I got it. Thanks. Mm-hmm.
Any remaining questions? If not, let's thank Carolyn again for this very nice talk. And we can now move to Gather Town, which I believe, Anna, can you post the link in the chat? And so we can have a more informal discussion if there was anything you wanted to ask but felt like it was too naive to ask, or anything